Welcome to part 2 of the section 2 lectures. So, in part 2, we will continue by looking at the next topic, which is disjunctions and conjunctions. So, when two statements P and Q are given, we might desire to combine them to produce a new statement. So a disjunction of P and Q is P or Q and is denoted by P and an upside down carrot top symbol Q. This is true if exactly one of P or Q is true, otherwise it is false. And a conjunction of P and Q is P and Q and is denoted by P and Q. So a carrot top symbol represents a conjunction of two statements. This is true only when P and Q are both true otherwise it is false. So now let's build a truth table showing these two new logical operations. So we'll put in the same truth values. And now we have the disjunction of P or Q. So when P and Q are both true, that's true. When P is true, Q is false, that's true. When P is false and Q is true, that's true. but it's false when both are false. And for the conjunction of P or Q, it's only true when both P or Q are true. All right, next topic we will look at is implications. So an implication is a statement where one statement directly leads to another. And this is written as if P then Q, or P implies Q. And this is denoted by P, and then we draw an arrow symbol pointing to the next statement, Q. So this is false only when P is true and Q is false. So let's construct a truth table showing this. So it is only false when P is true and Q is false. Another note, some other ways of writing P with an implication to Q. We can write it as Q if P, P only if Q, P is sufficient for Q, or Q is necessary for P. So let's look at an example. If we are given this statement, if 4 is even, oops, sorry about that, then 2 is even. Well, let's split this up into two statements. Let's say that P is, the first statement, 4 is even. Well, that statement is true. Let's say that Q is the second statement, 2 is even. And that is true. So P implies Q is true. And of course, we can also refer back to the truth table, and we can see that when P is true and Q is true, then P implies Q is true. Mathematics is more interested in statements containing open sentences. And if you recall from part 1, that's basically statements with variables. So we'll look at an example. Say we have a statement P1 of x, where x is 12, and P2 of x, where x squared is 144, where x is an integer. The following open sentences can be written. So, if we were to say not P1 of x, we could just write it as x is not equal to 12. Or, if we were to do the disjunction of P1 of x and P2 of x, we could say x equals 12, or x squared is 144. Or if we were to look at the conjunction of P1x and P2 of x, it would be x equals 12 and x squared is 144. Or if we were to look at P1x implies P2x, we would write it as if x equals 12, then x squared equals 144. All right, now we'll look at our next topic, and that will be biconditionals. So building off of implications for an implication, P implies Q, Q implies P is called a converse of P implies Q. So we will now define a biconditional, and a biconditional is the conjunction of an implication and its converse. So this is basically writing out what this would mean if we look at two statements, Q and P. And it is denoted by a double-sided arrow symbol. So let's construct a truth table to show this. Let's try to make that Q look a little better. So we'll put our truth values in here for P and Q. And then when both statements are true, the biconditional is true. But when the truth values do not match, it is false. So this is stated as P is equivalent to Q, or P if and only if Q. This is just writing out in words what the biconditional means. We also have P is necessary and sufficient for Q. So let's look at an example. Of a biconditional. So let's say we're given two statements, P, M, where M is a quadrilateral and Q, M is a circle. So if we were to write this out, as a biconditional, be written as M is a quadrilateral if and only if M is a circle. And let's say we are also asked what is the truth value of this statement? Well, probably the best way for this kind of statement would be to construct a truth table. So we have our two statements, P of M, Q of M. And remember, a biconditional consists of an implication and its converse. So we'll have to look at the truth values of P of M and Q of M. And also Q of M implies, sorry, I forgot to say implies with the previous one. And then we will look at the biconditional of M, of P of M and Q of M. So now this is kind of an example to give you an idea of constructing a truth table. When you're given statements like this, where you want to often break down like the biconditional into its components, the implication and its converse. Now, for this particular example, you may not have to do it, but just want to give a little more in-depth explanation for how this is done, because you will see a little later on that understanding a statement, especially if it has multiple parts to it, and breaking it up is crucial if you're needing to determine the truth value of it and you're constructing a truth table. Okay, so let's take a look at our statement up here. So we have M is a quadrilateral and M is a circle. However, when we look at our biconditional, M is a quadrilateral if and only if M is a circle. Well, the thing is, neither of these statements can imply the other, because a quadrilateral cannot be a circle and a circle cannot be a quadrilateral. So this is going to be either when P is Q or P is true, or P of M is true and Q of M is true, and the other is false. So we don't need to look at a specific case, because we can narrow it down to this specific column right here. And in this specific column, the biconditional only has a truth value that is false. So when P is true, Q is false, and when Q is true, P is false. So this particular statement is always going to have an opposing truth value to the two statements, which means the biconditional cannot be true. So this means that either one implication, or that either the implication P of M implies Q of M is false or true, and either its converse, Q of M implies P of M, is false or true. So therefore, just like we showed in the truth table a minute ago, the biconditional P of M implies Q of M is false. All right, that is it for part 2 of section 2. Thank you guys so much for watching. I hope this video was enjoyable and helpful to you, and I will see you in the next video for part 3.